So we'll see how far we get. Because this is kind of it. We're done with individual objects. Just a bit of a reminder. Friday we'll keep going with galaxies. We'll get to dark matter, which you guys know a lot about through insinuation and extra credit and stuff like that. Quiz 8 will be on Friday. The exoplanets practice quiz isn't up yet, but the black holes and high mass stars ones are. Quiz 8 will be exoplanets, high mass stars, black holes, and then next Tuesday at 3 p.m. We have UW Planetarium time. So I will leave this here. Is that the pin on Google Maps is if you type in Physics Astronomy Auditorium PAA, will take you to the giant bronze peanut. This is like a 2-story tall bronze peanut. So has something to do with physics, presumably. And there's a courtyard. This is the PAC building and the PAB building. You want the one across the courtyard with the big glass dome. Inside is a Foucault pendulum. And if you go up the circular staircase around the pendulum, the planetarium is at the end of the hall. If you show up a little bit late, we'll close the door at like 3:10 or something like that. Just bang on the door. So we've got to keep it closed because of light pollution and let people's eyes dark adapt. So easiest way to get there is I think the 49 bus will basically drop you at the College Inn where all the physics graduate students are, and then wander over to find the courtyard there. But then the Google pin is good enough. Okay. Any questions about that? Okay. So we're finally at galaxies. We'll talk a little bit about the line of evidence that, because you're born into this and you take it for granted that we live in a city of 200 billion, 300 billion stars called the Milky Way galaxy. And you've seen pictures of it. And now that you know how hard it is to even get off the face of Earth, you should be suspicious of anything that presents itself as a picture of the Milky Way galaxy. So I'll talk about the structure, and what you guys will do on the next exercise is go through one of the original arguments about why we live in, how we know we live in a city of stars, and how we know the distance to really far things. And then finally we'll weave together this thing where, it seems like we start as a cold cloud of gas, we end life, at least stellar life, as a hot cloud of gas. And we know that we have things like iron and uranium on planet Earth. So we will weave together the circle of life on a galactic way, and then a little bit about the formation of the galaxy. You'd kind of argue that the galaxy is still forming, but in some sense. Haven't seen this for weeks. This is the roadmap of the course. We're now through here, basically, and we're at our galaxy. But realize this took a lot of work because we had to talk about, classical astronomy, motions of the sky as perceived from Earth, the solar system and all the stuff inside of it, this zoo of objects in the Milky Way galaxy, all the different types of stars, all the remnants they leave behind. Now we know stuff about the planets that they have, and kind of quickly we'll actually go from there to here. So we're after 2 days of galaxies, we'll basically go on to cosmology and Hubble's law and modifications to Hubble's law. So this is what you see in this kind of patch of light with these dark splotches on it. So that's the Milky Way galaxy. Right? Everybody's seen this at some point in their life, I imagine, right? Hopefully. Takes kind of a clear day or night. And I just want to stop and impress you guys with the fact that to see this, and this in particular, and then argue that we're in the suburbs of a spiral galaxy 28,000 light years from a supermassive black hole with these arms and this bar structure and some globular clusters in the halo, this is not obvious, right? So in fact, even point of Galileo, people thought that this was something totally distinct. It wasn't even stars. So it took Galileo and his telescope to perceive the granularity of the Milky Way galaxy. So why is this hard? So 2 reasons, one of which we talked about before is the thing that's completely insidious and the bane of all astronomers everywhere, unless you study dust, then you love it, is dust. And this is the inside of a star-forming cloud, and it looks, black as ink because the light from the star-forming cloud will hit dust, and dust in particular loves visible light. So what seems to be true is the Milky Way is also associated with this nice dark dust lanes. There seems to be a lot of dust in it. The second reason it's hard to figure out where we live is, well, the Milky Way galaxy is, thousands of light years across, hundreds of thousands, depending on how you do your accounting. And we're not going to leave and turn around and take a picture. We're not going to see its shadow on some distant object. So it's really, imagine that you're locked up in Supermax prison and somebody asks you to sketch the outside. So that's an easier task, right? So we can't leave it, turn around. It's kind of like you're in a dark room and somebody asks you to draw your own face. You're kind of left with, poking around a bit. So how are we going to do this? And part of this is historical, even though we're spoiled again and we live in the modern era of, these technologically advanced telescopes, and we have access to all wavelengths of light, which will be the elevator to knowledge about the Milky Way galaxy. But historically, the argument went more like 2 and 3. So this evil, evil lane of dust is basically obscuring our knowledge. And one of the first breakthroughs, and the important part to take away from it is the variable star story and the distance ladder, is that people actually, if you can't see in the plane, you can look above and below the plane, and you can see clumps of structure above and below this central disk. So that was really the first big argument. And once you establish that we're kind of at the outskirts of this giant city of stars, and it's got a disk-like structure, then you can say, aha, there are all these disk-like structures out in the rest of the cosmos that kind of look like the thing that we seem to be in. I'll work really hard with variable stars again to figure out that these things are really, really far away, so they must be cities of stars like our own. And now we can study our own galaxy by looking at proxies and other spiral galaxies. So that's the historical argument. And we'll get there, and that'll be exercise 9. But right now, let's kind of take the express lane and just say, well, this is what the Milky Way looks like, a panorama in visible light. This is what it looks like in infrared light. And this stretches all around the sky. So does it look like we're at the edge of something with a disk and a bulge? Absolutely. So that's where we are. And we can figure out some more stuff, so I'll zoom ahead a little bit. This is basically long wavelengths to short wavelengths, so centimeter radio emissions, that means something kind of special. So it's radio emissions. There's a particular other type of radio that's associated with very, very, very cold gas. If you're going to be a molecule, you've got to be pretty cold. There's infrared, there's shorter infrared, there's visible, there's X-ray, and there's gamma ray. So highly energetic to low energetic. Look at any of these and tell me anything about the structure of the Milky Way, and then we'll piece the whole thing into the story itself. So what I already came up with is I look at visible light, and then I see a lot of dark bands, and I know that dust obscures visible light, so I know that there's a lot of dust in the plane of the Milky Way galaxy. So I look in infrared, and I see that it looks like off to one side, the place where we centered the pictures, there's a bulge, and then there's a plane. So maybe we're in a disk and there's a central bulge of the Milky Way galaxy that I can see once I use wavelengths that actually go right through the dust. So anything else that you notice from any of these? Yeah, there's some bubbles of gamma rays, right? So there's something crazy right here. It seems to have an X-ray counterpart too. And then looks like we have a bubble of gamma rays coming from the center of the Milky Way galaxy. But yeah, it looks like there's some energetic stuff going on. Some in the bulge, and then some at random, you can see it in X-rays too, some of these random spots around here. So X-ray, 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 X-ray bubbles. And they seem to be distributed all over the plane of the Milky Way galaxy. So our story needs to include energetic things happening all around us, at least where we are too. Good. Anything else? So where does our dust and molecule stuff accrue? Is it all over the place? Is it primarily in the bulge? Is it primarily in the disk? So it looks like we have a disk that's got the dust, and the disk has the molecules. And then the disk is also speckled with these really energetic sources like X-rays. So the big structure we get is this idea of a disk and a bulge and a halo, and the disk is completely full of dust, which obscures the visible light. And then there seem to be these really energetic events that we'll get to later. The stuff that I didn't show you is we could look above and below the plane, and there seem to be these things called globular clusters, which you've already seen in exercise 7. So huge clusters of stars that are very, very, very old. So the ones where you saw the horizontal branch, and then the hydrogen flash and the subgiant branch, and it was all perfectly articulated with hundreds of stars, and they were all pretty old, like 10, 12 billion years. Those are these globular clusters, and they tend to lie above and below the plane. And then finally, fast forward a little bit, if you do the work to find out the size of these things relatively, the entire Milky Way galaxy is about 100,000 light years across. So sit here, shine a laser pointer, it takes 100,000 years to get from point A to point B. You appreciate how hard it is to make some pretty movies of galactic simulations, is that, this is long light travel times. Most of the stars, however, are compressed into a really thin band. So the disk with the dust and most of the new stars, especially the star formation, is about 1,000 light years across, which is not that much, especially compared to the distance. So this 100 to 1 aspect ratio, thickness to width, that's kind of like a compact disc or a DVD or something like that. So imagine a DVD, hold it up. It's basically where most of the visible light and the stars in the dust of the Milky Way are. The bulge and the globular clusters just seem to be overrepresented because, again, the evil, evil dust, which obscures everything. So the principal parts you can call disk, halo, where the globular clusters and some other things live, and then the bulge is the central kind of puffy part. And it turns out, you guys will actually find your own number for this, but we're about 28,000 light years from the center of the bulge, and this is where the supermassive black hole lives. Okay. And then within that, there are spiral arms, which we'll talk about in a couple of minutes. So that's what we figured out so far. And you should know these parts and maybe be able to sketch a picture of a spiral galaxy like our own, including distances. Any questions about that? Yeah, it's not. They're shades of gray, so you can have a very strong bar-like structure in the center of a spiral galaxy. They're called barred spirals, somewhat uncreatively. And there can be completely amorphous, perfectly spherical blobs. And we have more of a bar than a perfect spherical bulge. So sometimes you will say the bar-like bulge or something like that. But probably the opposite. So we'll talk about galactic evolution on Friday. And it turns out that Hubble had this idea that was totally informed by the theory of evolution, that if you take a really amoeba, amorphous, lumpy-looking, completely undifferentiated elliptical galaxy, and you put it in a jar and you let it go for 10 billion years or something like that, you would evolve into this beautiful spiral galaxy. But that's actually not the case. So we were made like this and will continue to be like this until Andromeda comes and smashes into us and ruins everything. So we're born in, as a spiral galaxy, and until we interact with Andromeda, we'll remain so. So over the course of their lifetimes, barring interaction, galaxies don't really change that much. So. Yeah, so it's possible that other people know this and can say it with authority, but I don't know, and my impression is that there's no understood consensus exactly of how the black hole, supermassive black hole at the center of a galaxy forms, in the sense that people aren't sure if it's a consequence of all the stuff coming together and you start making this structure, and then because you have all this stuff swirling around, eventually you make a black hole, or if there's a primordial black hole that causes the galaxy to form around it. So I think you can simulate either, and you can simulate a galaxy forming without a black hole. But I don't know if there's some consensus among astronomers about that. So it's kind of hard to tell, actually. What people do know is that the black holes were much more active in the distant past when galaxies were first forming. And it's also true there's an analog that if you ever find a snowflake in Seattle, at the center of every snowflake there's a little piece of dust which nucleates the ice crystal around it. So maybe the black hole is the piece of dust around which the galaxy forms. But I don't think there's a complete and well-accepted theory about that. We do have one, though. Yeah. Actually, everybody seems to have one. Every galaxy. Okay. So each of these areas, disk bulge halo, they have their own types of orbits. These are a little bit exaggerated. But you don't need to know anything new to understand them, aside from the fact that the rates are a little bit off, which is the dark matter problem. If you're a globular cluster and you're way above the halo, you basically execute this highly inclined, probably pretty elliptical orbit. So the entire, billion mass of stars in the giant cluster is actually orbiting around the center. In the bulge, there's probably more interactions among other things, and the orbits are also pretty inclined and also pretty elliptical and a little bit more chaotic. What we're doing, and this is a bit exaggerated, is that we are orbiting a solar system like ours out in the suburbs of the disk, is orbiting around the center that takes about 250 million years, but we're a little bit off-center, so we actually bob up and down like a carousel horse. And there are some pretty goofy theories that say like every 35 million years when we bob up and down, we run into clumps of dark matter or gamma rays, and if you look at the extinction history of life on Earth, there's a whiff of periodicity at 35 million years, so we'll think that this horsey motion is actually why, like the dinosaurs were killed and stuff like that. I wouldn't bet money on it, but people think these things, and we do bob up and down a little bit too. So it's not a perfect Keplerian orbit. Okay, so if you were to do some galaxy tourism, you'd actually notice that stars are not just stars, and if you were in the disk and looking at a globular cluster, or if you were in the star field, you would actually see much different composition of stars. So this is a typical globular cluster. This is a giant one, actually, M80, which means that Mr. Messier saw it. What can you tell me about the stars in this cluster of galaxies? In this cluster? Yeah. So is this cluster really old or really young? Really, really, really old, right? And so I look at a dense star field in the disk, I might see something like this. What can you tell me about the stars in the disk comparatively? So I see that, that. So if I see a blue star, I know that something's happening, right? So probably the star forming that's going on here is much more active because I see blue star means it's got to be pretty young, like less than 100 million years or something like that. So this is characteristic of the disk. That's characteristic of the halo. What is the disk got that the halo doesn't have? So this is a place where you can do what? Form new stars, right? So these need to be young, and this is associated with all those like popcorn-like bubbles that you saw in the X-ray spectrum. Is that this is the energetic place? Okay. So if you actually were to use the methods of exercise 7 to date this cluster and look for the, make the temperature brightness chart and look for the main sequence turnoff point, you would get that this is a 12 billion year old cluster. So this is really old. Even G stars like the sun, our sun, are long died, billions of years previously. If you were to, so that's great. Pretend that you're an astronomer for a second. What's the next thing that you want to do? You want to figure out what's going on in a cluster like this. It's like the knee-jerk reaction for an astronomer is, I don't know what to do, so I should take a spectrum, yeah. If you take a spectrum, what you notice is that these are actually very, very, very metal-poor stars. Good. So you don't see a lot of iron, you don't see a lot of calcium, stuff like that. Is that these are first or second generation stars. And kind of, stands to reason they're pretty old, but they're also really metal depleted. Conversely, in the in the disk, you would see star fields, lots of blue stars, therefore younger, and then spectra say that they're totally enriched with metals. So, random star from the disk and a random star from the halo would probably be remarkably different. So those are the observations. So now the question is, how do we weave this all into some story about either how this was formed and what it's doing? And this is the story that explains everything. This is good news because we see a lot of other galaxies, and this is not controversial. I'm not giving you something like nebula theory that I'll have to retract half of later. So turns out that the story that makes sense of this actually kind of paints a picture of a galaxy as like kind of an ecosystem, and there's a tundra and a desert and kind of a green area, and then there's this almost like archaeological site up in the halo that describes what happened 12 billion years ago when we first formed. But before we do that, I'm just going to, you guys kind of know it, but I'll just say it so it's on the record, is that we're going to close the loop on star life and star death. So this is a star-forming cloud. It's a really cold cloud of gas, and it's enriched with metals, and it forms something like our star. We know that metals like helium and neon and iron and neon and heavy things, they come from the cores of short-lived, very massive stars. Carbon comes from lower mass stars, but at the end of their lives, whether it be a supernova remnant or a planetary nebula, they blow up. So stars' life begins with cold gas, ends with hot gas. How do you turn hot gas into cold gas? You wait. What does the universe have plenty of time to do? Wait. So this is actually a cycle, and the cycle is called unsurprisingly enough, the star-gas-star cycle. So these are the stages, but again, this is stuff that we've already done. Just realize that this is constantly happening, and this is kind of like a crank that you turn, where you have a cold cloud of chemically enriched gas, collapses into a new star burns merrily along. Its solar wind will start returning gas into the cosmos. It might go supernova or leave behind a planetary nebula, returning hot, even more chemically enriched gas. The gas will cool down, turn into clouds. Those clouds get so cold, maybe they'll even make molecules. The fact that it's molecules helps the clouds collapse a little bit. It's not terribly important. But it's really hot cloud, cold cloud, repeat. And every time that you turn this crank, you get more and more iron, more and more carbon, more and more metals. So this is happening inside, in particular, in the disk of the Milky Way galaxy. And in fact, simulations and some data tell you that this happens in kind of a weird way, is that this stuff will actually burst out of the disk of the Milky Way galaxy in this kind of mushroom cloud. So this would be a supernova going off, and maybe 30,000 years after the supernova goes off, it breaches all the gas and the dust in the plane of the Milky Way galaxy, comes up, and the gravity of the stuff, the matter in the disk itself, pulls stuff back down. So there's almost like this cloud of chemically enriched gas that's had time to cool down, just falling back down to seed new star formation. And there's some evidence that we actually live inside of one of these bubbles. They expand very quickly. So this is even the supernova that went off in 1006 AD. It's 60 light years across. And all it's got to do is get to about 1,000, and it'll blow its way through the disk of the Milky Way galaxy. So yeah, the energy it requires to do this, it's not necessarily like escaping from Alcatraz in the sense that when we talk about dust and gas in the plane of the Milky Way galaxy, it's not that much. I mean, if you remember, you computed the density of interstellar space on like exercise 5 or something, right? Do you remember how absurdly small that number was? 10 to the minus 24 grams per centimeter cubed. So this isn't really a hard fight to fight, so it just expands until it finally pops its way out and then gets pulled back down. So you mean how fast does this stuff cool down before it's serviceable for a star-forming cloud? Yeah, I think that would depend on what you are. So planetary nebula, you cool down faster. Supernova remnant take a longer time. And I don't know offhand, but you do have to get down to about 30 degrees Kelvin before you can start making new stars. So I'll just conservatively say 100 million years or something like that, but I don't know offhand. It kind of depends on the circumstances of the gas, I think. So, planetary nebula, not that hot, so that'll cool off in about 10,000 years to the point where we can't even see it. But a supernova remnant, I mean, that's a really powerful thing. Okay, so we can get more specific, and we can see exactly where this stuff is happening. This is a galaxy that looks kind of like ours, and I see the dust lane, so where the dust is obscured, and we can zoom in on that. So this is the dust lane where dust is obscured. And where do you see these stars blowing up like popcorn? Is it in the spaces in between the spiral arms? Or the back edge of the spiral arms? It's basically like the leading edge of the spiral arms. So there's something about the spiral arms, and you can see this rash of star formation and explosion and cold clouds of gas, is that seems to be where all of the star-forming action is. So yeah, stars form in the disk more than the halo, but if you want to get really specific, it's the spiral arms. And when we get to what the spiral arms actually are, you'll see why. So in fact, what you're seeing is an incredible, billion-car pileup going on. So look at dust extinction, and then look at colors, so bright patches of stuff. And yeah, absolutely, the story about star formation works. Okay. So the next interesting feature of at least our type of galaxy, and there are other types of galaxies, are these things. And they're very pretty, but there's something of a quandary in the spiral arms. So let's pretend that you're some, supernatural being, and you're able to just float in the middle of intergalactic space and observe one of these for, we'll call it, 2 billion years, right? So that's certainly enough time for something there to orbit about 10 times or so. What do you think this galaxy is going to do over the course of a couple billion years? And let's just pin it down to some options. So do you think I painted this galaxy on a plate and I'm just spinning the whole thing around uniformly? Does that kind of break some laws that you guys learned about how things orbit? So who spins around the sun faster, the Earth or Neptune? Earth, because it's closer to the center in the mass, right? So Kepler's laws would tell you that, up to the fact that you're including a little bit more mass, the closer you are, the faster you should spin. The farther out you are, the slower you should spin. So what would that tell you about these spiral arms if it was like, the spiral arms were composed of the same stars? So what would they seem to do? So the inside would spin faster than the other one. Yeah, it would like wind up like a clock, right? So do you guys think that these things actually like wind up like a clock? Or do you think they're more of like rigid rotation? I'll play rigid rotation because it's kind of hard to describe. But it's really, imagine that I painted it on a I would not have thought to describe it like that, but yeah. So take an octopus on an ice rink and spin it. Here we go. I'm very happy with that analogy. It's good. Let me go here. See if this will. Okay, here we go. Good. So this is rigid rotation. This is the idea that if I sit here for 2 billion years and I look at this galaxy, it's like it was painted on a dinner plate and somebody's just spinning the dinner plate. This is kind of what you think that you should see. To each their own, but this is kind of what I thought should be happening. Okay, so this is what Kepler's laws would tell you. If Kepler's laws said that these things, start with some local overdensity or something like that, is that this thing would exactly wind up. And you would start with a galaxy that had, very normal-looking arms, maybe 2 arms, but as the inner stars spun faster and faster, they would get wound up. And then you would have this like super whirlpool corkscrew spiral galaxy. And we absolutely do not see this in any other galaxies that look like our galaxy. So this isn't quite right, but the thing that you want to be right actually violates Kepler's laws. So what's going on? And just to show that is this is Kepler's laws is that the thing that's closer would go faster, and now you just imagine that this is like the supermassive black hole and these are stars. The inner stars would spin faster, and so they would wind up the arms, which absolutely you don't see. So what's going on? Any suggestions about how to resolve this? Okay. The first thing you said, repeat that. So what did we ignore when we just set things into motion with Kepler's laws? Is that things actually interact with each other. Now I told you all quarter to not worry about it. Now I'm going to retract my statement. So what we're not talking about is individual objects interacting with individual objects. So this isn't, stars bumping into other stars, because the grapefruit model still is totally valid. I have a grapefruit here and a tangerine in New York City as a representative density of what's going on. So we're not interacting gravitationally, but this teeny tiny flimsy amount of dust and gas actually is the culprit. And when you're in a spiral arm, you actually move a little bit more slowly than you would otherwise. And for most intents and purposes, it's not important. But what actually ends up happening is they set up traffic jams. And I like this a lot for some reason, is they just told these people who devised this experiment, I don't know, is they got a bunch of folks and said, listen, just drive at 30 kilometers per hour in a circle. That's all you have to do. So you have the simplest instructions possible. Just drive in a circle at 30 kilometers per hour. And of course, you know what happens.
For the first time, Japanese researchers conducted a real
British accent, that's great.
Shows how some traffic appear for no apparent reason. They placed 22 vehicles on the track, asked the drivers to cruise around at constant speed, 30 kilometers an hour. At first, traffic moved smoothly, but soon the distance between cars started to vary, and vehicles clumped together at one point on the track. So the jam spread backwards around the track, at a shockwave at a rate of about 20 kilometers an hour.
Okay, so this is the important part, is pick a car and follow it as it makes it to the traffic jam shockwave. So here it is. So maybe pick this blue car. Blue car makes it to the traffic jam, is in the traffic jam. Blue car fights its way through the traffic jam. Blue car is free. Traffic jam persists. So the traffic jam itself is one thing, but then the cars participating in it are different every time. This is the spiral arm of the Milky Way galaxy and other galaxies. Is the spiral arms themselves are a traffic jam, and different stars participate in it or not. And so you can keep your Kepler's laws, but if you add in this slight perturbation where you get to the back of this, there's a little bit more dust and gas. Maybe there's a supernova that goes off near you and really increases the local density. You slow down, you fight your way through it, you leave. You're not in the spiral arm anymore, but the spiral arm itself is a persistent structure. And the reason it took people so long to realize this is because when you look at this, you're really not witnessing or you're not able to resolve individual stars. So this is what's called density wave theory. And I'll show you an animation because I actually really like this one. Let's make this as high res as possible. That's all we get. Great. So try your best to follow an individual star as it makes it to a spiral arm, fights its way through and leaves. It's actually almost like mind-bending. So maybe this guy moving really fast. Oh, they're good. Zoom in. So make it there, fight your way through. Now you're free, but the spiral arm, aka traffic jam, exists behind you. Okay. So what you don't see is, and this is another video of the same thing. This one's the super trippy one, I think. Is that the structures persist, but the stars participating it don't. And in fact, when you're in one of the spiral arms, your life is pretty dangerous because there's a lot of new star formation, and there's consequently a lot of supernovas going off around you and stuff like that. Okay. So any questions about that? So if you were this very long-lived creature and you chose to watch a galaxy for 2 billion years, this is what you would see, is the whole thing kind of keeps the same shape. But then the stars that are actually blowing up and moving through are different every day. Okay. So quick note about habitability, and I don't mean in some geologically alive or dead sense. I literally mean, if you were to find a habitable star exoplanet. The bulge is a terrible place. There's a supermassive black hole. In a day-to-day basis, it's not a problem. But the orbits are chaotic. There's a lot of radiation. It's a tough place to live. So you actually wouldn't really expect to see a lot of long-lived, stable planets around the bulge. In these middle galactic latitudes, so maybe from here to here, there's a sweet spot that people actually call the green zone. So there's enough star formation that there's chemical enrichment, and there are things that are the building blocks of life, like oxygen and iron and carbon and stuff like that. But you're not so close to the bulge that you might get in trouble. So the way that somebody described it once to me was that imagine that you need the ashes from a campfire to live, because that's what we need. We need iron and things that are the ashes of this thermonuclear campfire. There's a lot of ash there, but then that's also where the fire is. Here's this kind of nice spot where we're close enough to get the byproducts of thermonuclear fusion and supernovas, but we're not so close that one's going to get us. And then finally, out in the far galactic latitudes, you can kind of think about it almost like a tundra, where there's just so little star formation going on. There's just not enough stuff to chemically enrich and form potentially habitable planet. So we are in a very lucky spot, actually. So we have interesting stuff which is created in this set of violent events, but we don't have so many violent events that we may have gotten destroyed by something yet. So nearby supernova that caused us to form about 5 billion years ago, and there's some evidence that a couple of really big ones went off like 50 million years ago, so it happens. Okay, any questions about that stuff? Lucky until we're unlucky. So the theory of the formation of the galaxy, we actually have all of the relevant physics, and we're going to totally recycle this, including the jet, which is missing from this. Shame on them. They should know by now. The only difference is, for a single star, a single planetary disk, is you have a big cold cloud of gas, collapses, angular momentum has it spin out into a disk. There's a jet, there should be a jet there, and then voila, you have this spinning disk-like structure. So first time we talked about it, it was star in the middle, planets at the outside. I'm just going to steal that and say that's our theory of how a galaxy forms. And we know that this is a good story because during this phase, during the collapse into a disk phase, during this entire process, stars were being formed. And these really, really, really old globular clusters that speckle the halo, they're actually the remnants of that really early phase of life. And now we can actually date our entire Milky Way galaxy. Because the globular clusters formed about 12 billion years ago. This period of time before we collapsed into a disk and we still had gas and dust that were making stars up there was 12 billion years in the past. There's other evidence that supports that too. But this is actually the globular clusters. They're the remnants of the first stars ever formed before the Milky Way actually even spread out into a disk. Okay. So the first little correction to that is that it's not like a totally uniform cloud of dust like that, or gas. We actually kind of came together like, this is a really dated reference. You guys ever watch Voltron? Too young, all too young. Anyways, like these things, and they come together to make a comically oversized robot that they... Yeah, Power Rangers ripped off of Voltron. It's garbage. But yeah, that thing. So it's not a single unified cloud of gas. Apparently there were these baby galaxies that were each struggling their way through the cosmos, and the baby galaxies came together. There's some evidence where if you look at the chemical composition from different parts of our Milky Way, it's kind of patchworky. So it's like we're quilted together from these dwarf galaxies. The other bit of evidence we have that this is what happened is we're actually still eating dwarf galaxies, which was not discovered until recently. So on the far side of the galactic bulge, There's the Sagittarius dwarf galaxy, because it appears in Sagittarius. That's where the galactic center is. And there are a couple of other ones, too. So the Magellanic Clouds orbit us. We're actually eating a couple of these so-called dwarf elliptical galaxies. So it's still happening. And this is where we get new dust and gas that actually fuel more star formation. So that's actually pretty new. There's another thing called the Monoceros Stream, which is not a full galaxy, but a clump of stars, which is being pulled into the disk of the Milky Way and spun out and being set into fuel for creating new stars. Okay, so that's us, and we did that in a sort of ahistorical way, where I just said, this is what's going on. What we'll do on the 9th exercise is trace the historical argument, because it introduces us to the miraculous power of variable stars, which we're going to need for the distance ladder and cosmology later. So we'll pick up with that on Friday. Any questions about any of that stuff? Okay. Yeah. I have them printed off if you guys want to pick them up now, sure. But I won't really go through it until Friday, because it's all about